So previously we had calculated the equation corresponding to the entropy or the average information per symbol. As you know that it is also called as the source entropy. Some of the books will represent this as H of S, okay, in the entropy of the source. It's still the same, right? We can, if we want bits per symbol, take a log to the base 2 of this above equation, right? Otherwise we can change the log to the base, right, as per the required unit of measurement. Okay, so after that, the next important concept is what is called as the information rate. So the rate at which we receive the information is what we are trying to calculate here. That is the information rate denoted as R. Okay, so this R is going to be calculated by using two parameters. One is the small rs and the capital H. Okay, so this capital R is the information rate. We know that the H is the entropy, and this rs is called as the message uh, per second, okay, or the symbols per second. It's called as a symbol rate, right? So let's try to measure the unit for R. So what is the unit for RS? It's a symbol rate. You can say that this is symbols per second. That's the first term. I multiplied this with H. Okay, H is the information per symbol, right? Information in the sense it can be bits, it can be any other parameters per symbol, right? So you can see that the symbols will get cancelled, right? And I'm left out with bits, that is the information per second, correct? So you see that the note, the unit for this will be bits per second, or if you measure in decits per second, or nats per second, as per the equation. Okay, but the R is actually measuring the information per second. In 1 second, how much information you receive. Okay, so that's very important. So equation is capital R information rate is equal to the symbol rate small letter r into the capital H, which is the entropy. Okay, let us try to calculate. Let's go for a problem first. Okay, right. Okay. This is the problem. A discrete information source emits 8 symbols every millisecond. In 1 millisecond, it is going to emit 8 symbols. Okay, 8 symbols in this. Right. There are 5 possible symbols with the probabilities 1 by 2, 1 by 4, 1 by 8, 1 by 16, and 1 by 16. Calculate the source entropy and the information rate. This is the question. Okay, so first part is pretty straightforward. The h can be calculated directly. So there are 5 different symbols that are possible. Okay, so I is equal to 1 to 5 pi into log. We calculate in base 2 itself. Okay, 1 by pi. So all the 5 symbols have to be used. First one is half log to the base 2 of 2 plus 1 by 4 log to the base 2 of 4, 1 by 8 log to the base 2 of 8 plus the 1 by 16 is 2 times. So 2 times 1 by 16 log to the base 2 of 1 by 16. Okay, please calculate this h value. So 0.25 into log 4 to the base 2 is 2. Correct. Next is 1 by 8, that is 0.125. Okay, and this value will be 3. Then 2 times 1 by 16 is 0.0625 into 1 by 16 to the 1, sorry, uh, I wrote it wrong here, mistake. I'll correct this. So it's just 16, right? Sorry. Okay, so that is 4. So simplify this, you should get the answer. So when you simplify this, we get 1.875, and the unit is bits, average information, bits in a symbol. So bits per symbol. Okay, fine. Now I need to calculate the information rate. Information rate, capital R is equal to small r into h. Anyway, h we have. I just need to calculate what is the small r or rs. So this is what it's the number of symbols per second, right? So you see, they say that there are 8 symbols, right? In the question, you can see that 8 symbols are sent in 1 millisecond. So in 1 second, how much? So this is what I need to calculate. That's what is the in 1 second. We denote that as, instead of question mark, I can simply write that as rs. Correct? So 8 symbols in 1 millisecond, rs symbols in 1 second. So how do you calculate? Rs into 1 millisecond is 8 into 1. So 8 divided by 1 millisecond. 1 milli is 1 into 10 to the minus 3. So that is 8 into 10 to the 3. So that will be 8,000. Okay, 8,000 symbols per second is the rate. Now you calculate. Therefore, right, the information rate, okay, what's called as, it's r, right? So therefore capital R, it becomes equal to rs into h. Rs is 8,000 into h is equal to 1.875. Please calculate. This is equal to 15,000. What is the unit? Bits per second. It's a rate, right? Information rate. So we measure in this fashion. Okay, so we'll move on to the next level of problem, right? Normally, this what we solved, we have solved now is a simpler one, okay? But what might appear in the questions will be slightly complex, but not very difficult. It's easy, okay? But they try to represent the data in a different format. That's all. Okay, so okay, so this is the question: the output of an information source consists of 150 symbols. Okay, out of the 150, say 32 of which occur with a probability of 1 by 64, and remaining symbols occur with a probability of 1 divided by 236. Okay, if the number of symbols emitted per second is 2000, calculate, find the entropy and the information rate. This is the question. Per symbol. Okay, that is HFS. And what is the information rate? RS is equal to small rs into h. That gives you how much? Can you repeat the answer? 2.64 bits per second. Right, so that's the correct answer. Right, let's move further. So we have the similar type of questions being repeated all over. Okay, so maybe you can try to solve the ones which are repeated in your papers, and maybe, right, if you have doubt, you please let me know. Okay, so then the next topic that we are going to discuss will be the properties of entropy. Right, So we have several properties. We'll start with the property number one. So the first property says that the entropy will be a continuous function of the probability. Entropy is a continuous function of probability. Right? So it means if I try to plot the probability versus its entropy, it will be a continuous function. Okay, so that's anyway, we will be trying to prove this by means of problems. Okay, so let's go to the second property. Let's list out the properties first. Right. The second property is that entropy will be a symmetric function of the arguments. That's the second property. We'll verify this later when we solve some problems. Okay, entropy uh, is a symmetric function. So entropy of a system is the same irrespective of the order in which the symbols are arranged. Whichever symbol comes first, that comes later, doesn't matter. Entropy remains same. That's what is the meaning. Okay. Then again, to prove this, we have to solve some problems. Direct proof is not available. But for the third property, we can go for what is called as a proof. Okay, so we'll prove the third one now. That is, this is called as the extremal property. There is a name for this, EXTREMAL. It's extremal property, or the extremal property is used to find what is called as the upper bound uh, on entropy. What is the highest value of entropy? That's what we are going to find now. So the properties statement is like this, right? Okay, let me get the statement first. Okay. If Q symbols are sent with equi okay, I'll write equal probabilities. That's more suitable word. With equal probabilities, then the h of s reaches a maximum value. Okay, it's going to reach a maximum value, and that maximum value will be equal to uh, log to the base 2 of q. Right, so only when you have all the symbols, if it is three symbols, you have equal probability 1 by 3. So q symbols are sent with equal probabilities of 1 by q, right? Then the h of s, or h becomes h takes its maximum value. Okay, so that's what is the meaning. All right, so let's try to prove this. Right. So let us initially say that they are not equal. Okay. Let's say there are many symbols being transmitted, but they are not going to have the equal symbol, equal probabilities. Right. So this is the proof. Let Q symbols are emitted. Say S is equal to, let's try to write them. They are S1, S2, and all the way till SQ. Okay, those are the various symbols that we are trying to send. So those symbols are being sent with the probabilities let's denote that as P is equal to P1, P2 to PQ. Q symbols with the Q different probabilities. Okay, so P1, P2, P3 up to PQ. Right. Now, if at all I want to calculate the entropy of this, right? Therefore, the entropy. How do you calculate the entropy? Entropy is H or H of S. That is equal to summation starting from I is equal to 1 to all the symbols, that is Q symbols. This is Pi log to the base 2 of 1 by Pi. Is it okay? Right? This is what we already know. I also know one more thing. I will write it here. And what is the sum of all the probabilities? That is I is equal to 1 to Q. If I take the simple sum of all probabilities, that should be equal to 1. Correct? Right. So this is what we already know. So one of the symbols will definitely appear. So sum of the probabilities will be equal to 1. Okay. Now, so if we want to calculate the upper bound, we will consider the following term. Okay, so the upper bound is calculated using this. So to find the upper bound, let us consider. So I'm going to consider this term, that is log of Q minus this H of S. So how do I calculate log Q? For consideration of the log Q, I'll write that I can try to write this as 1 into log Q. That 1 I am going to write it as I is equal to 1 to Q Pi. Okay, that is 1 into Q, not Q, sorry, into log Q minus what is H of S. Write the equation for H of S. That is I is equal to 1 to Q. It is Pi into log of 1 by Pi. Right? It is very straightforward. Right? Now I actually purposefully put that summation I is 1 to Q in the first term. Right. Now that summation is common for me. So what I do, I'll try to take that common term out. So I is equal to 1 to Q. The Pi is common for us. Right? Once you take it out, what remains here is log Q, first term. Second term, log 1 by Pi. Okay. Now I know from the properties of log, I can write like this: summation I is equal to 1 to Q Pi. So you see log Q, the minus I can make it plus if I take the Pi in the denominator to the numerator. So this is simply log Pi. Okay, so log Q plus log of Pi. Right? So log A plus log B is log of AB, isn't it? So this is I is equal to 1 to Q. This is Pi log of, this is Q times Pi. All right. Okay. Now, so let me try to understand a concept that let's say this is it log to the base 2. Okay, so whatever log I have taken so far is to the base 2, right? So how do I write a log to the base 2 in terms of any other log, say log to the base e, right? I can use a property, right? So that means, so let me try to write uh, let the log of q, that is on the left hand side, minus h of s. This is already present on the left. So I'll write here, this is what I was calculating, log q minus h of s, right? So this is what I had calculated so far. I have been calculating. So I got this. Now, if I want to change the base of my log, right? So how do I do that? It's log to the base 2. If you want to convert that into log to the base e, this is the equation, right? So summation, say I is equal to 1 to q, pi remains as it is, only log changes. Log, it is natural log, so ln of e of q times pi divided by, it is log to the base e, or ln I can write, no problem, ln of 2. Is it okay? Right, log 2 to the base e. Right, now I can actually move this up and I can write, so log 2 to the base e can be written as log of e to the base 2 in the numerator. You can move it up. Then you write summation, say I is equal to 1 to q, right? It is pi times natural log ln of q times pi. Why I represent it like this? We have a reason for that. Let me call this as equation number 1. Okay, so just to understand what we are trying to do, I need to draw a graph. Okay, so let me draw the graph first, then we'll look at this in detail. So just see, right? First, we'll consider a straight line, that is y is equal to x minus 1, right? So this is the y-axis and this will be the x-axis. Now, in order to draw this line, I need to first put x equal to 0. When x equal to 0, y is minus 1. So that will be somewhere here. Okay, this is y equal to minus 1, y equal to minus 2. Let me write some of the values, x equal to 1, x equal to 2, x equal to 3, and so on. Similarly, I might need x equal to minus 1, minus 2, minus 3 as well. Let me draw a few points on the positive y-axis, 1, 2, etc. So this will be the origin. Okay, now, so when I want to find the y-intercept, put x equal to 0. So y is minus 1. That means the straight line is going to pass through this point. Right? Similarly, put put y equal to 0, you get the x-intercept. Right? So x equal to plus 1. So this is the line which we are talking about. Okay, so let me try to draw this line as accurately as possible. Okay, maybe, right? This is the most appropriate straight line. Okay, so this is the line that is y is equal to x minus 1, right? I'll justify this, why I am trying to draw this. And I also have, I want to plot another curve. So that is the y is equal to natural log of x. Okay, so that curve will be, maybe I'll change the color. That curve will be something like this. Okay, so this is the curve, y is equal to natural log ln of x. Now I understand that except the point x equal to 1, in every other position, right, the ln of x is lesser than the curve y equal to x minus 1. Right, so I'll justify why I'm using this slightly later, but let me use whatever we learned through this graph. first. So from the graph, so we understand one thing, that is natural log of a function x is either lesser than or only at one point it becomes equal to, right? That is y equal to x minus 1. Okay, so which means minus of natural log of x should be greater than, because you're multiplying by minus, so right, sign will change, it is 1 minus x. Okay, so that means I can write minus, I can take inside, so that is natural log of 1 by x will be greater than or equal to 1 minus x. Fine. Okay, now let's go to the uh, point where I'll make a substitution. Right, let me hold on. Okay, no, I'll put this. So if the x is equal to 1 divided by q times pi, whatever this term we know now, already we have used it. This implies, I'll replace the equation with this. So ln of 1 divided by q into 1 by q into pi, so that becomes q into pi in the numerator, right? So this should be greater than or equal to 1 divided by, it is x is equal to 1 divided by q minus pi. This is true for any equation, so I'll call this as 2. Okay, now what I do, I multiply both sides of equation number 2. I multiply both the equation, both sides of equation 2 by the pi, and I'll also take a summation. Okay, so I'll write what I'm doing. Multiply by pi and taking the summation. Right, what happens? Let's try to do this on equation number 2. Right, I'll get summation, that is I is equal to 1 to q have pi into ln of q times pi. This should be greater than or equal to, right, the summation I is equal to 1 to q, we have pi multiplied by 1 minus 1 divided by p times, is it right? Oh no, it's q times pi, my mistake. Q times pi. Are you okay with this so far? Now what I do, I multiply both sides by log to the base 2 of e, because I'm trying to compare this with, right, this is what I want to bring. Okay, so I need a log to the base 2 of e, right? So this implies log e to the base 2 summation I is equal to 1 to q pi ln q into pi should be equal to the log to the base 2 of e into summation I is equal to 1 to q p times 1 minus 1 by q times pi, and I'm going to call this as equation number 3. Let's hold on to this and we'll come back. All right, so the last step is that, right, I'll try to compare this with equation number 1, right, because log q minus h of s, right, should be always greater than 0, because then only I have, right, some, I'll look at this. So the log q minus h of s, right, always should be greater than 0. That's what we understand from equation number 1, correct? So I'll try to write an equation. Right, I'm trying to compare equation number 1 with the equation number 3. So you see the right hand side of equation number 1, is nothing but it is the left hand side of equation number 3. Correct? So when I do pi into 1 minus 1 divided by q minus pi, that should be, right, at least that should be greater than 0. So I'll compare. So from 1 and 3, I can come to a conclusion that the LHS, that is log q minus this h of s, should be greater than or equal to 0. Right? What is the meaning of that? That implies the h of s is always lesser than or equal to the log q. Are you okay? Now, you see, that means what is the highest value of this? It becomes equal to means it is that value, correct? So, that implies the maximum value of h of s. Max value of h of s is the hs max, correct? So, that is h of s max is equal to simply the log q. Right? So if you have q symbols, right, I can say that the probability is 1 by q. Right? So log of 1 divided by 1 by q is log q. So maximum value of the h of s will be, right, log of q, where q is the number of symbols. If you have 3 symbols, log q to the base 2 is the maximum value of h of s that can happen. Right? Depends on the q value, how many symbols you are sending. If you have 5 symbols being generated, the highest value of h will be log to the base 2 of 5. Okay, log 5 to the base 2. Like that, we calculate the h's value, maximum value. So by using this particular property only, we will be able to understand that. Okay, so I'll make one final comment over here. Right? Therefore, the entropy attains maximum value, I'll underline this, when the source symbols are equiprobable. So that is important. Maximum value comes into picture only when you have equal probability among the symbols. So that finishes this particular property.